Tell me, which of the processes occur at a faster rate? Rusting of iron pipe or burning of cooking gas? Of course, you know the answer. Rusting is a slow process and burning of LPG occurs at a faster rate. Then, what about photosynthesis? Photosynthesis occurs at a moderate rate. Thus, we can say that chemical reactions can occur at slow, fast or at a moderate speed. In this video, you will learn about chemical kinetics, the branch of chemistry which deals with the rate of chemical reactions. The word kinetics comes from Greek word kinesis, meaning movement. Consider a chemical reaction where 1 mole of the reactant R produces 1 mole of the product P. Initially, the reaction medium contains the reactant alone. As the reaction proceeds, concentration of the reactant decreases and that of the product increases. For a time interval, delta T given by T2 minus T1, if the decrease in concentration of the reactant is R2 minus R1 and the increase in concentration of the product is given by P2 minus P1, then the average rate of reaction can be defined in terms of the change in concentration of the reactant or product with respect to time. That is, the rate of decrease of R will be equal to minus delta R by delta T, and the rate of increase of product P will be equal to delta P by delta T. The average rate then would be given as shown here. The average rate of reaction can be depicted graphically as shown here. In fact, the average rate does not predict the rate of reaction at a particular instant of time. The average would be constant for the calculated time interval. In order to obtain the rate of a reaction at a particular instant of time, instantaneous rate is determined. Here, an infinitesimally small time period, say dt, is considered. That is, when delta t approaches 0, the slope of tangent in a concentration versus time plot gives instantaneous rate. If the change in concentration of reactant and product are dr and dp respectively for an instantaneous time interval dt, then the instantaneous rate is given by minus dr by dt, which is equal to dp by dt. When A moles of A reacts with B moles of B to give C moles of C and D moles of D, then the rate can be expressed as the rate of disappearance of any of the reactants or the rate of appearance of any of the products divided by their respective stoichiometric coefficients, as you can see here. From these discussions, I hope you are clear that rate has units of concentration bar time. Hence, rate can have units of mole liter inverse second inverse or atmospheric pressure second inverse. Now, we will look into the concentration dependence on the rate of reaction. The dependence of reaction rate on concentration of reactants and products is represented as a rate law. For the reaction displayed here, the rate equation can be written as rate is directly proportional to the concentration of A raised to x and B raised to y. That is, rate equals K A raised to x B raised to y, where K is called the rate constant. Here the x and y may or may not be equal to the stoichiometric coefficients A and B of the reactants. This expression is called the rate law. The rate law can have different forms which we will discuss later. It has to be clearly understood that the rate law for reaction can be determined only by experiment and not from the balanced chemical equations. Meaning, the value of exponents x and y can be determined only experimentally. In fact, exponents x and y are described as the order of the reaction with respect to the reactants A and B respectively. And the sum x plus y is called the overall order of the reaction. Order can have values 0, 1, 2, 3 and even fraction. Hence, you may deduce that rate constant can have different units depending upon the order of the reaction. For a reaction of order n, you may say rate constant can have the units of mole raised to 1 minus n, liter raised to n minus 1, second raised to minus 1. Next, we will discuss the molecularity of a reaction. A reaction that takes place in a single step is called elementary reaction. Those reactions which can occur in a series of 2 or more steps are called complex reactions. Each step in such reactions gives the mechanism of the reaction. Molecularity may be defined as the number of reacting species involved in an elementary reaction which must collide to bring about a formation of products in a chemical reaction. Based on the molecularity, reactions can be of different types. Unimolecular reaction involves only one reacting species, for example, decomposition of ammonium nitrate. Bimolecular reactions involve collision between two species, as in the case of dissociation of nitrogen dioxide. Trimolecular reactions involve three species, for example, formation of nitrogen dioxide. Reactions having more than 3 molecules are very rare, and this we will discuss in collision theory. Now tell me, the relation between the slowest elementary step in a chemical reaction with the order and molecularity of that reaction. With this, I will summarize this video.
Manorama Horizon. Learning made simple.